Hi, my name is Kate, and today I'm going to tell you a little bit about what cells eat. In my world, this stuff is called media, and so I'm going to talk to you a little bit about its role in cultured meat production. So first, we have to ask the question, what is media? Media is food for cells. Here in this flask, we can see some animal cells that are stuck to the bottom of the flask and the rich, nutritious bath of media that floats on top of them, giving them everything they need to survive and thrive. So the more complex a cell is, the more complex the media is. So simple cells like bacteria only really need the basics to survive and thrive. These things like salts, sugars, vitamins, minerals, proteins, and fats. And yeasts are much the same. They only really need the basics to survive. When we start looking at more complex cells, like insect cells, they need even more ingredients to survive and thrive, like cholesterol and hormones. And when we start to talk about some of the most complex cells, such as animal cells, they need all of these basics, and then cholesterol, hormones, and even more specialized proteins. These are the cells that we need for cultured meat production. This cultured burger was tasted live in London in 2013. And this is what it took to make it. So when we start to consider the vast quantities of cultured media that are required to make even one cultured burger, we start to realize how crucial it is to have an inexpensive, sustainable source for cultured media production. So what is in animal culture media? This is Dilbeco's Modified Eagles Medium, or DMEM for short. Its ingredients are pretty standard. Inorganic salts, which are ions that balance the cells and keep them from bloating in the media. Amino acids, which are the building blocks of proteins. Vitamins, which help the cells function metabolically. And glucose, the energy source of the cell. And last but not least, fetal bovine serum, or FBS, or what I like to call the secret sauce of animal cell media. So, what is FBS? Literally, FBS is fetal bovine serum. So fetal bovine serum is a fraction of fetal cow blood. So when blood is harvested from a cow fetus, it's spun in a centrifuge, and the stuff that rises to the top is fetal bovine serum. It's a rich mixture that contains everything a growing cow needs to survive and thrive. And that's part of the reason it's so incredible for medical research. Scientists have been using it for a long time because it works well, but not because we know what's in it. So what is an FBS? While we don't have a comprehensive understanding of the ingredients of FBS, we can start to group the things that are in FBS into definite categories. The first category is hormones, which are small molecules that are essential for cell signaling. The second is albumins, which are the largest class of blood protein. And then globulins, which are fully folded blood proteins, followed by attachment proteins, which mediate the connections between one cell and another, and the connection between cells and their substrates, like plastic. And then other regulatory proteins, such as growth factors and other special high-value proteins. And then on top of this, even more proteins, some of which may not even yet have fully elucidated functions. So now that we have a basic understanding of what is in cultured media, we can start to understand some of the problems associated with it. First of all, it's expensive. Second of all, it's animal-derived. And third of all, it has some variability because it is, in fact, animal-derived. As we can see, all of these issues with current animal cell medium result from the fact that it contains fetal bovine serum. So, what can we do to replace fetal bovine serum in medias? And how do we go FBS-free? There are some products on the market that can help us avoid fetal bovine serum. One of these is UltraSear, which is a product that is essentially a proprietary replacement for fetal bovine sera in media. It's used in medical research. There are other specialized medias as well that can be used with particular contexts in mind, for instance, in neuroscience. However, these particular types of media are only useful for one type of cell, for instance, a neuron, but they wouldn't work for another cell, like an animal cell. So what about cultured meat? How do we bridge this gap and start to understand how we would create a media for our cultured burger? So if we think about current FBS media, it's proprietary, which means we don't know the recipe that it's used, and it might even contain animal products, if not FBS. It's also cell-specific, which means it works for one particular type of cell, like a cancer line or a nerve line. It's also expensive. 500 milliliters can routinely cost $40 to $50 in a laboratory environment. This is opposed to our ideal animal culture media, which is animal-free, meaning that it's completely vegan. It's also open source, meaning that its formula is freely available online for people to use and for people to improve upon the recipe. It's also cross-compatible, which means that it would work for multiple different types of cells. And it's also inexpensive enough that cultured meat can become a reality. So there are some similarities between the current available medias and what we have that would be our ideal culture media, and that both are FBS free and both have high functionality, meaning they consistently work exactly the way you want them to. And they're consistent formulations in that we know exactly what's in them, and that does not vary. They're also modular in that you can add and subtract components as necessary to tailor your media to exactly what you want it to be. So if we are going to think about how we would make our ideal cell media, we can take essentially a three-step approach. First, we can define what's in FBS. Second, we can determine which components are ultimately necessary from FBS. And third, we can replace those components when possible with cheaper, greener alternatives. So if we're going to think about how we define FBS, we can group the different categories of things into some different groups, the first of which are things that are very easy to define, like inorganic salts, amino acids, vitamins, and glucose. These are super quantifiable and very easy to define. Others, like hormones, we might have to do a little bit of poking around in the scientific literature, but we can find that information. Albumins are pretty well-known blood proteins, as are attachment proteins, globulins. It gets a little more challenging when we start looking at things like regulatory proteins and other proteins, which are much harder to define in our media. So if we think about how much protein is in FBS as compared to non-FBS medias, we find that FBS-containing medias have 16 times the amount of protein on average as non-FBS-containing medias. This is really interesting because it suggests that FBS is a super rich, nutritious bath of things that basically contains more than we need for our ideal culture media. So it's highly likely that our ideal formulation would have much less protein than FBS does. It would have closer to half a milligram per liter of proteins rather than the whole 8.1 average for FBS-containing medias. I do want to point out, though, that certain components of FBS are really essential for mammalian media, and they're what makes mammalian media such a special mixture that works so well for animal cells. So what components are necessary? How do we start figuring this out? What we need is open source research on what ingredients are necessary for cultured meat. In addition, research at specific academic institutions can help us figure out the underlying biology that's at play and help us understand how to grow sustainable muscle cultures. These goals are really the goals of New Harvest in many ways, in that we really want to obtain this open source, fully sustainable culture media recipe that could be used and developed further by others as well. So if we're going to start thinking about how we replace these components and how we could definitely make this ideal media, some things are really off the shelf, like inorganic salts, amino acids, vitamins, and glucose. Some things can be synthesized through chemistry if we want to make them animal-free, like hormones. This process has already been done at scale if you think about things like birth control pills, for example. Albumins can likely be substituted for things like peptone and tryptone, which are simple yeast proteins that are very inexpensive. Some things require more like bespoke manufacture, such as attachment proteins and globulins. Others require novel bespoke manufacture, such as certain regulatory proteins and other proteins if we are to make them at scale. These would in fact require research and development to obtain a method for making them in bulk that we could use. In addition to this, animal proteins need decorations. So if we think about our mammalian proteins that we need for cultured meat production, they're much more like our iced gingerbread man as opposed to our uniced gingerbread man, in the sense that they need these special additions to be added to them using special cellular machinery once they've essentially been made. Bacterial cells are only capable of making the simple gingerbread man without frosting, whereas more complex animal cells would need those special decorations that can be added through the special machinery that a more complex cell has. For example, the protein Fabrazyme that's made by Genzyme to remedy a genetic disorder that results in an absence of alpha-galactosidase in cells is really specialized in that it needs to be made by insect cells, which have all this advanced cellular machinery that can add the sugar decorations that decorate this complex human protein. I just want to point out the cost is not trivial. I got really interested in the cost of different serum proteins that might be available, so I started looking on online laboratory catalogs to see how much it would cost to buy these reagents if we wanted to currently. And while I want to point out that these are not at-scale production costs at all, it is very interesting that albumins and attachment proteins can be made in fairly for much less money than things like globular proteins or regular proteins, which do in fact have a rather high price point. However, there's another path forward that really doesn't involve any of this reductionist approach, and it's called co-culturing. So in co-culturing, one cell, like the pink cell, makes a protein that the other cell needs, like the blue cell, to survive and thrive. So if we imagine that the pink cell is, say, a liver cell, it can produce a protein with its advanced cellular machinery, spit that out into the cell media, and then that protein can be uptaken by the muscle cell, which needs this particular high-value protein to survive and thrive. If we think about doing this at scale, we can start to see how much value we could generate in creating all these novel proteins from one particular type of cells to help another grow. There are a whole lot of advantages to co-culturing. One is that, in theory, it's very much cheaper than producing individual proteins recombinantly. Another is that it really is a one-shot deal and that it can add a whole lot of proteins at once to a culture media. The downside, however, is that it's still mysterious and that we wouldn't know exactly which factors were contributing to the value of this particular additional cell type. So, like FBS, it's still a somewhat mysterious approach.